Hello guys and gals, and welcome to the first video on section 5.9, which is about the steady state approximation. There will definitely be several videos for this section because it's not really something that we can honestly understand without doing several examples of it. So for this first video, all we're going to do is introduce the idea of what steady state approximation is and go over what equilibrium is and how that plays a role in reaction mechanisms. And we'll save the examples for exactly what we're trying to do in the next videos. So 5.9a says if the first elementary reaction is not rate limiting. So if you've got a reaction mechanism and the first step is not the slowest, it is not rate limiting, approximations such as steady state must be made to determine a rate law expression. So if your first step is not rate limiting, or if you have something called equilibrium involved in your rate or in your reaction mechanism, we have to use something called the steady state approximation to determine the rate law for the overall reaction. So the steady state approximation says that because we are making the assumption that an intermediate in the reaction mechanism is consumed just as quickly as it's generated, we can use the rate of that intermediate, the rate of appearance and the rate of disappearance for that intermediate to determine the overall rate law of the problem, of the equation. So basically it implies you select an intermediate in the reaction mechanism, calculate its concentration, not with numbers, but in formula. So calculate the formula, do some algebra to determine the formula that we could use to solve for its concentration, just because we can assume that it is consumed as quickly as it's generated. Most of the time, steady state approximations are necessary for reactions that contain an equilibrium system. Reaction is at equilibrium. This means that the reactants are making the products at the same rate that the products are making the reactants. So in this case, a reaction that is capable of being at equilibrium has to be reversible. When it is at equilibrium, the forward reaction, making the products, and the backward reaction, or the reverse reaction, are happening at the same time, in the same container, and at the same rate. And so here's a very common equilibrium expression that we use in industry almost every day to make ammonia. The nitrogen and hydrogen gas produce ammonia at the same rate that the ammonia breaks back down into the nitrogen and hydrogen gas. And so eventually they'll reach a part where they're just making each other as fast as they are breaking back down, and your concentrations don't change. And that's how you know that you're at equilibrium. Notice that the yield sign is different. It's pointing in both directions now to tell you that the reaction is occurring in both directions at the same time. And so you can also see either of these two other arrows. Those are actually a little more common than the one I used in the equation here. So that is about all that we have to introduce steady state approximation. Most of the time on the AP exam, it's going to be with reaction mechanisms that include equilibrium, but it can also be with reaction mechanisms in which the first step is not rate determining. And we're going to use that intermediate, and we're going to find the rates of appearance and disappearance of that intermediate to determine the rate law of the overall reaction based only on the reaction mechanism and not any experimental data. Okay? So we will do some examples in the next video, and please let me know if you have any questions.